Chapter 6.5 Introduction to Queuing Theory. One of the greatest concerns of traffic engineers is the serious congestion that exists on urban highways, especially during peak hours. This congestion results in the formation of queues on expressway, on ramps and off-ramps, at signalized and unsignalized intersections, and on arterials where moving queues may occur. An understanding of the process that lead to the occurrence of queues and the subsequent delays on highways is essential for proper analysis of the effects of queuing. The theory of queuing therefore concerns the use of mathematical algorithms to describe the processes that result in the formation of queues, so that a detailed analysis of the effects of queues can be undertaken. The analysis of queues can be undertaken by assuming either deterministic or stochastic queue characteristics. Deterministic analysis of queues. The deterministic analysis assumes that all of the traffic characteristics of queue are deterministic and demand volumes and capacities are known. There are two common traffic conditions for which the deterministic approach has been used. The first is when an incident occurs in a highway, resulting in a significant reduction in the capacity of the highway. The second is a significant increase in demand flow exceeding the capacity of a section of highway, which can be described as a varying demand and constant service rate condition. Varying service rate and constant demand. In figuring out the service rate and constant demand, these are the several important parameters that can be determined to describe the effect of this reduction in the highway capacity. First is the maximum queue length, or Q max, is the excess demand rate multiplied by the duration of the incident and is given as Q max is equal to quantity V minus CR times T. The V here is the demand volume, while the CR is the reduced capacity, multiplied by T vehicles. The time duration of the queue, T sub Q, is the queue length divided by the difference between the capacity and the demand rate and is given as T sub Q is equal to the demand capacity minus the reduced capacity times T over the demand capacity minus V. The average queue length is Q sub AV is equal to quantity V minus reduced capacity times time over 2 times vehicle. The total delay, D sub T, is the time duration of the queue multiplied by the average queue length and is given as D sub T is equal to quantity V minus C sub R times T over 2 multiplied by quantity C minus CR times T over C minus V is equal to time squared quantity V minus reduced capacity times C minus CR over 2 times C minus V times hour. Let's use this example for queue length and delay due to an incident on a freeway using deterministic analysis. A 3-lane expressway is carrying a total volume of 4,050 vehicles per hour when an incident occurs resulting in the closure of 2 lanes. If it takes 90 minutes to clear the obstruction, determine the following. A. The maximum queue length that will be formed. B. The total delay. C. The number of vehicles that will be affected by the incident. D. The average individual delay. Assume that the capacity of the highway is 2,000 vehicles per hour per lane. Solution. First, let's determine the capacity of the highway. Let's multiply the 3, being a 3-lane expressway, by the capacity of the highway. Therefore, the capacity of the highway is 6,000 vehicles per hour. Next is determine reduced capacity of the highway. 2,000, the capacity of the highway, multiplied by 3 minus 2, since an incident occurs resulting in the closure of 2 lanes. Therefore, the reduced capacity is 2,000 vehicles per hour. Next is the duration of the incident, which is 90 minutes or 1.5 hours. Determine the maximum queue length. Q max is equal to total volume times reduced capacity times T vehicles, which is stated in the problem. There is a total volume of 4,050 minus the 2,000, which is the reduced capacity of the highway, times 1.5 vehicles is equal to 3,075 vehicles. Letter B. Determine the total delay. dt is equal to 1.5 squared multiplied by quantity 4,050 minus 2,000. This 4,050 is the total volume stated in the problem, while this 2,000 is the reduced capacity, multiplied by 6,000 minus 2,000. 6,000 being the capacity of the highway and 2,000 is the reduced capacity, over 2 multiplied by 6,000 minus 4,050. This 4,500 here is an error in the book, but I substituted with 4,050, but they have the same answer, which is 6,150 hours. Letter C. Determine the number of vehicles that will be affected by the incident, which is equal to 4,050, which is the total volume given in the problem, multiplied by 1.5, which is the duration of the incident, or 1.5 hours, which is equal to 6,075 vehicles, being the number of vehicles that will be affected by the incident. Letter D. Determine the average individual delay. This is obtained by dividing the total delay by the number of vehicles affected by the incident. 6,150 is our total delay over 6,075 vehicles, the number of vehicles that will be affected by the incident. Therefore, our average individual delay is 1.010 hours. Stochastic analysis of queues. Using a stochastic approach to analyze queues, consider the fact that certain traffic characteristics, such as arrival rates, are not always deterministic. In fact, arrivals at an intersection, for example, are deterministic or regular only when approach volumes are high. Arrival rates tend to be random for light to medium traffic. The stochastic approach is used to determine the probability that an arrival will be delayed, the expected waiting time for all arrivals, the expected waiting time of an arrival that waits, and so forth. A queue is formed when arrivals wait for a service or an opportunity, such as the arrival of an accepted gap in a main traffic stream, the collection of tolls at a toll booth, or of parking fees at a parking garage, and so forth. The service can be provided in a single channel or in several channels. Single channel, undersaturated, infinite queues. So this is the figure of a schematic of a single channel queue in which the rate of arrival is Q vehicles per hour and the service rate is capital Q vehicles per hour. For undersaturated queue, capital Q, and the rate of arrival, small q, assuming that both the rate of arrivals and the rate of service are random, the following relationship can be developed. First, the probability of n units in the system P quantity n. P quantity n is equal to rate of arrival over the service rate to the power of n multiplied by 1 minus rate of arrival over service rate, where n is the number of units in the system including the unit being serviced. Next is the expected number of units in the system, E quantity n. E quantity n is equal to rate of arrival over the service rate minus the rate of arrival. The expected number of units waiting to be served in the system, E quantity m, is equal to rate of arrival squared over the service rate multiplied by the service rate minus rate of arrival. Note that E quantity m is not exactly equal to E quantity n minus 1. It's because there is a definite probability of 0 units being in the system. Next is average waiting time in the queue. E quantity W is equal to arrival rate over service rate multiplied by service rate minus arrival rate. The average waiting time of an arrival including queue and service, E quantity V, is equal to 1 over service rate minus arrival rate. Probability of spending time t or less in the system. P quantity V is equal or less than t is equal to 1 minus e to the power of negative 1 minus arrival rate over service rate multiplied by arrival rate times time. The probability of waiting for time t or less in the queue. P quantity W is equal or less than t is equal to 1 minus arrival rate over q multiplied by e to the power of negative 1 minus arrival rate over service rate times arrival rate times time. Next is the probability of more than n vehicles being in the system. That is P quantity n, or the number of units in the system, is greater than the number of vehicles. P quantity n is greater than vehicles in the system is equal to rate of arrival over service rate to the power of n vehicles being in the system plus 1. Let's use this example. Application of single-channel undersaturated infinite queue theory to a toll booth operation. On a given day, 425 vehicles per hour arrive at a toll booth located at the end of off-ramp of a rural expressway. If the vehicles can be serviced by only a single channel at service rate of 625 vehicles per hour, determine the percentage of time of the operator of the toll booth will be free, the average number of vehicles in the system, and the average waiting time for the vehicles to wait. Solution. We have an arrival rate of 425 vehicles per hour and a service rate of 625 vehicles per hour. So in order for the operator to be free, the number of vehicles in the system must be 0. So instead of putting value here, we substitute it with 0. So the probability of in units of the system is equal to 1 minus arrival rate over the service rate, which is equal to 1 minus 425 over 625, which is 0.32. The operator will be free 30% of the time. Letter B. We are asked to find the expected number of units, which is equal to the arrival rate over the service rate minus arrival rate, which is equal to 2. Next is the average waiting time of an arrival, which is equal to 1 over the service rate minus the arrival rate, which is 0.005 hours, or which is equal to 18.0 seconds. Single channel undersaturated finite queues. In the case of a finite queue, the maximum number of units in the system is specified. Let this number be capital N. Let the rate of arrival be small q and the service rate will be capital Q. If it is also assumed that the both of the arrival and the rate of service are random, the following relationship can be developed for the finite queue. Probability of n units in the system. The probability of n units is equal to 1 minus probability over 1 minus probability to the power of number of vehicles plus 1 multiplied by probability to the power of n units, where probability is equal to the arrival rate over the service rate. The expected number of units in the system is equal to the probability over 1 minus probability multiplied by 1 minus number of vehicles plus 1 multiplied by probability to the power of number of vehicles plus number of vehicles multiplied by probability to the power of number of vehicles plus 1 over 1 minus probability to the power of number of vehicles plus 1. Example. Application of single-channel undersaturated finite queue theory to an expressway ramp. The number of vehicles that can enter on a ramp of an expressway is controlled by a metering system which allows a maximum of 10 vehicles to be on the ramp at any one time. If the vehicles can enter the expressway at the rate of 500 vehicles per hour and the rate of arrival of vehicles on ramp is 400 vehicles per hour, during the peak hour. Determine A. the probability of 5 cars being on the ramp, B. the percent of time the ramp is full, and C. the expected number of vehicles on the ramp during peak hour. Solution. A. the probability of cars being on the ramp. Q, which is our arrival rate, is 400 vehicles per hour, and the service rate is 500 vehicles per hour. And our probability is equal to 400 over 500, which is 0.8. Using the formula, probability of n units is equal to 1 minus probability over 1 minus probability to the power of n, which is the number of vehicles, 10 plus 1 multiplied by probability to the power of n units. Therefore, the probability of 5 cars being on the ramp is equal to 0.072. Next is the probability of 10 cars being on the ramp. Using the same formula, let's substitute 5 to 10 because we're asked to find the probability of 10 cars. So P, quantity 10, is equal to 1 minus 0.8 being our probability over 1 minus quantity 0.8 to the power of 11. 11 comes from the number of vehicles plus 1, which is 10 plus 1, multiplied by probability to the power of 10. Therefore, the probability of 10 cars being on the ramp is 0.023. Next is the expected number of vehicles on the ramp. The expected number of vehicles is equal to probability over 1 minus probability multiplied by 1 minus the number of vehicles plus 1 multiplied to probability to the power of number of vehicles plus number of vehicles multiplied by probability to the power of number of vehicles plus 1 over 1 minus probability to the power of number of vehicles plus 1. Therefore, the expected number of vehicles on the ramp is 2.3. 97, or the expected number of vehicles on the ramp is 3.